Okay, thank you. Good morning, everyone. I'm Tomohisa Kawashima from National Institute of Technology, Ichinoseki College in Japan. Today I'll be talking about the high-energy neutrino emission based on the GRMHD simulation. And the paper is here and published yesterday. Okay, I will start my talk with introduction of high-energy neutrino. Why high-energy neutrinos are important? It is because the acceleration mechanism of the high-energy cosmic ray is still uncertain, as is explained in today's morning two invited talks. And the cosmic ray acceleration, high-energy neutrinos are cosmic ray acceleration, smoking gun, and this is some processes, PP collision and P gamma processes, and the pions are produced, and then the gamma ray and the neutrinos are also produced. And cosmic rays their trajectories are bent by magnetic field, and gamma rays are optically thick against background light in some times. But the neutrinos freely propagate towards us. So neutrino is a very good smoking gun of the cosmic ray acceleration. There are two types of cosmic ray, thermal origin or non-thermal origin, that can be divided by roughly their energies of neutrino. The thermal origins are produced by the thermonuclear reaction, and basically it is produced in the high density environment. For example, supernova explosion, gamma ray burst, stellar interior, and so on. And the messenger of the stellar interior and governing the dynamics of the explosion and burst, this is the case of the thermal neutrino that can be observed by Super Kamiokande and so on. On the other hand, hadronic process of cosmic rays produce non-thermal neutrino, and because it requires the acceleration of the particle, the low density environment is preferred. For example, supernova remnant, active galactic nuclei, jet of low luminosity gamma ray burst, and so on. These are the messenger of cosmic ray acceleration and the test of the elementary particle physics. And these type of neutrinos are observed by IceCube and so on. So we focus on this type of high energy neutrino. Okay, so here's the possible origin of the extragalactic high energy neutrino. Of course, recently the galactic neutrino are detected by IceCube observation. But we are focused on extragalactic one because we are interested in those type of neutrino. And here the diffuse neutrino observed by IceCube collaboration. It will be addressed later. And there are still uncertainty of the origin of the extragalactic high energy neutrino, active galactic nuclei, galaxy cluster, starburst galaxy, and the low luminosity gamma ray burst. Okay, so it's important to consider the origin of the neutrino, and diffuse neutrinos SEDs are important observational quantities to address the problem of the cosmic ray acceleration. And here the diffuse neutrino spectrum, and the typical Pavlov index is about 2.46. And interestingly, this is flatter than that of the neutrino hotspot that is observed in NGC 1068, that is a type of the Seyfert galaxy. And because the spectral flux, the Pavlov index is slightly harder in this diffuse neutrino, so we can expect that various types of neutrino SED may exist. And as I explained, there are many types of the candidates of the diffuse neutrino background, but we focus on AGN here because we are interested in supermassive black holes, since the neutrino hotspot is also the supermassive black hole. And models of the neutrino emission in AGN are here: accretion from origin and disk corona origin model, and disk wind model, and the wig jet model here. And we consider relatively inefficient accretion flow model for low luminosity AGN in this work. Okay, here's the purpose of this work. The problem is that although there exists pioneering work on neutrino emission model in accretion flow, but a single zone model approximation has been adopted in all of the previous works. So we cannot expect what occurs when the global structure of the accretion flow is taken into consideration. So the question is, how does the global structure of the accretion flows affect the neutrino SCDs? So the purpose of this work is studying the global effect of the accretion flow on high energy neutrino SCD, considering cosmic ray acceleration by a kinetic scale turbulence in the accretion disk and neutrino emission by a proton-proton collision process. And there are no numerical code to calculate such a global structure effect. So we have developed a new code to calculate cosmic ray acceleration and the neutrino emission that is called the new RICO code. And that is adapted to the 3D GRMHD simulation data. Okay, here is the overview of the calculation method. We assume the black hole mass equal 10 to 8 solar mass, and m dot is 10 to minus 2 L18 over c square. And we calculate the trajectory of the tracer particles of cosmic ray protons by post-processing 3D GRMHD simulation data. And we compute the SCD of cosmic ray protons by solving Fokker-Planck equations with phenomenological turbulence model, turbulent acceleration model. And then we calculate the neutrino SCD assuming PP collisions with GRMHD protons with the gravitational redshift effect. And then we update delta T in the simulation, and sometimes snapshot will be also updated. But we do not incorporate the effect of the feedback of the cosmic ray to the hydrodynamics in our work. Okay, we will explain a bit detail about the computational method. So here the trajectory of the tracer particles of cosmic ray protons, and cosmic ray protons are treated as tracer particles. Here are the 3 examples of the trajectory of the cosmic ray proton. And we assume that the cosmic ray protons moves along the streamline, being trapped by subgrid scale turbulent B field. And we are interested in acceleration up to TeV, and we treat the region of the gyro radius is smaller than the mesh size. So we show some invalid energy range in the resultant SCD in later. And the GR data set of semi-mod, that is moderately magnetized state simulation by using the GRMHD code Uwabami, developed by Takahashi-san. He's one of my collaborators. Okay, we compute the SCDs of the cosmic ray proton by solving the Fokker-Planck equations here. And the turbulent acceleration with hard sphere approximation is assumed in our work. And we assume that the diffusion coefficient in momentum space is proportional to the, the significance of the turbulent-like structure here. And injection of the cosmic ray proton, which may be triggered by the reconnection, are treated as like this one. So there is a change. If there is a change of the B field, then the injection rate becomes also larger in our calculations. And the compression expansion effect are also included in our work. We note that there are two free parameters in our calculation. So here is the acceleration efficiency and injection efficiency. And we set these parameters as 3 times 10 to 5 and minus 5 and 10 to minus 3 for our fiducial model. So this is type of minus 5. Okay, then we calculate the neutrino SCDs, and PP collisions are assumed as I explained before, and the PP collision that is accelerated by solving proton accelerated proton that is calculated by solving Fokker-Prandtl equation is assumed to collide with the thermal protons of GRMHD simulation data. And Kellner's analytic formula, semi-analytic formula, and cross-section of Kama et al. Are assumed in our calculation. And the gravitational redshift are taken into account, and the normalization of the time average mass accretion rate onto the black hole, and the outflow rate is assumed, and to normalize the SED of the neutrino emission. And in our work, no viewing angle dependence is considered here. Okay, here is the result of the time average neutrino SEDs. So it is interesting to say that the SEDs are flatter than one-zone models, and as we showed, the one-zone model spectra is like here, that is a bump-like structure SED, but we found the flatter SED. This is because of the summation of the various SED of the neutrino and the cosmic ray proton, and I will show that later. And we note that in this shaded region, the streamline treatment is not valid in the light gray region, and the P gamma processes are non-negligible in the dark gray region. Okay, so please consider only the white colored region in this domain. And we also decompose the origin of the decompose the SED of the neutrino by the origin of the cosmic ray proton. So inflow cosmic ray proton origin is shown in red color, and blue shows the outflow cosmic ray proton origin, and green one is the residual ones. And so we found that the neutrino originated from finally outflow cosmic ray proton is more significant than the inflow cosmic ray proton origin. So here we show the cosmic ray proton trajectories and time scale. We show 3 types of cosmic ray. Inflow cosmic ray proton that is finally swallowed by the black hole, and the outflow cosmic ray proton, and the outflow cosmic ray proton, but it was inflowing in early stage of the trajectory. So we find that the cosmic ray proton SED becomes harder when the cosmic ray proton stays in the accretion flow. And the time scale is evolution is here as a function of the radius of the simulation domain. And it is well accelerated for the case of the inflow cosmic ray proton origin. Outflow cosmic ray proton shows less accelerated feature because the time scale of the staying inside the simulation domain is shorter in this case. But I have to, I'd like to say that for the case of the initially inflowing cosmic ray proton and finally finally it is finally outflowed, then the time scale is larger. It remains inside the simulation domain longer than this one, this type. So the spectrum of the cosmic ray proton becomes harder compared with this KSP. And it is very important to say that the cosmic ray proton SED depends on the position and the trajectories of the cosmic ray proton. And so the summation of the various SED results in the SED that is flatter than the one-zone approximation model. Okay, here the time scale, escape time scale from the simulation domain. It is the m dot c square as a function of the residual time scale inside the simulation domain. The red one shows the inflow origin, and blue one shows the outflow origin, and green one is the residual ones. And we showed the time scale of the accretion assuming this parameter alpha equal 0.1 and 0.001 to estimate typical accretion time scale. Of course, we solved the MHD simulation, and we do not require the alpha parameter of the disk model, but it is shown just, how to say, it is shown just for the, how to say, to compare the result with the accretion time scale. Okay, due to the long stay of the outflow cosmic ray proton in the simulation domain, as is shown in the previous slide, this case, so the acceleration well works for the outflow cosmic ray proton origin. So how the SED is obtained compared with the inflowing proton origin. So here the dependence of the acceleration and injection coefficient. I explained that two free parameters of the our calculation, efficiency of the acceleration and efficiency of the injection. So we make 3 times larger acceleration efficiency, then we obtain the harder and large luminosity of the resultant neutrino. And the injection, for the case of the injection, if we set 3 times higher efficiency for injection efficiency, then the low energy part becomes brighter, but the high energy part becomes dimmer, less brighter. This is because the higher injection rate results in the higher cosmic ray energy, and then the, how to say, the energy density of the cosmic ray becomes larger, then the acceleration time scale becomes larger, and so the efficiency of the acceleration becomes less effective. Finally, we showed the comparison between the neutrino, ice cube diffused neutrino background. So we integrated the neutrino SED of our model, assuming the luminosity function of Ho et al. 2008, and assuming that the neutrino luminosity is proportional to m dot c square. And we obtained the resultant background neutrino as here, and the ice cube neutrino result is here, the purple one. And we find that the case of the higher injection case, this dashed line case, with the combination of the NGC 10 to 68 types neutrino emission may explain the background SED of the high energy neutrino. So here the prospect, we will also develop the sophisticated acceleration and injection models in future, and free time dependent calculation of the neutrino emission using, for example, magnetically arrested disk. And it may be useful to consider the ice cube detection or discovery of TX S05 plus 6 plus 56. And also we have developed a code of the calculation of the radiative transfer in multi-wavelengths, RICO code. So we will combine this code and to calculate the P-gamma processes in future work. In the summary, we first attempt to compute the cosmic ray proton acceleration, the neutrino emission of global accretion flow based on 3D GRMHD simulation data. And due to the global effect, the flatter SED appears and it may partially explain the diffuse neutron background. And in our result, neutrino emission, which is originated from outflowing cosmic ray, accelerated in the inflow, predominate the SED. And more developed work will be carried out in the future work. Thank you very much.
Okay, questions? Heike.
Thanks for the talk. I have two questions. One is, as far as I understood, these are essentially you put test particles in the MHD. So from that, how can you repeat again? How do you reconstruct the full luminosity of the neutrino signal? So that's the first question, and then the second one is about the losses, because I noticed you've taken pretty high accretion rate. It was somewhere like 1%. So in that case, because this acceleration that you considered, if I understood, is also very slow, do you really expect that the losses will allow you to get to those energies?
Okay. Please let me confirm your question. The first question is how to calculate the neutrino luminosity by using test particle. Okay. So as you mentioned, some okay, yes. Normalization is required for the test particles. So we set the normalization like this one, and this is the weight of the test particle that is proportional to the mass inside each meshes, which is where the test particles are generated. And we sum up these test particle, and we also use the for the case of the inflow cosmic ray origin, we use the m dot mass accretion rate onto the black hole that is time averaged. And so we can set the normalization and calculate the neutrino luminosity. So the test part. Yes, essentially m dot. Yes, yes. The second question is, okay, let me ask again about the second question. Sorry.
Second question was about, because this process is rather slow, do you expect, especially in the regime you're considering for high accretion rate, about 1%, do the losses, high losses or anything else, do they not matter at all?
Okay, thank you. First of all, I'd like to mention that the m dot c square is, okay. M dot c square is between here, so m dot is 88 over c square times 10 to minus 2, and I'd like to mention that it is how to say upper limit of the Lyrac, and not the standard disk. How to say the standard disk does not appear in this regime, and I think it is marginal, and so we are still not sure how the efficiency of the acceleration is, how significant in the marginal limit of the Lyrac. But so, it is still collisionless, and the particle acceleration can occur in the supermassive black hole environment.
Chris? Thanks for the nice talk. So, to some people, that's actually a very low accretion rate, 10 to minus 2. And in that setting, I suspect that the gamma rays that are produced will escape, unlike very compact corona, because relatively photon poor area. So the question is, have you looked at whether gamma ray background constraints are consistent with this picture for the neutrino background?
So I have not yet addressed the detailed calculation of the gamma rays due to the hadronic processes. So, but I examined the, briefly examined and roughly checked, and I found that a similar SED of PP processes, due to the PP processes, and gamma ray emission should be a bit higher than the neutron emissive luminosity. And of course, it may, we can obtain some gamma ray background, but we do not incorporate the effect of the pair creation or something like that, and it may affect the gamma ray emission. So we have not yet still, we cannot still constrain our model by comparing the gamma ray background. So I will address this in future work.
I guess Chris's question boils down to whether you can hide the gamma rays that you produce alongside these neutrinos at these accretion rates. So, yeah.
I have a couple of questions. So just so I understand, the connection between step 1 and step 2 on this slide. So are you inferring the diffusion coefficients from test particles and then solving the Fokker-Planck equation? What's that arrow from 1 to 2?
1 to 2, you mean?
Yeah, that one.
Sorry, gamma?
The arrow you're pointing at right now. What is actually being done in this step?
Okay. So we, step by step calculate these 1 to 3. And in one, snapshot and certain t time, we update the position of the tracer particle by changing delta t.
Sure.
And during delta t, we compute the, integrate the Fokker-Planck equation.
But to do that, you need diffusion coefficients.
About the diffusion coefficient, we use the, local value of V and thermal energy of the GRMHD particle, proton particles, and the cosmic ray proton that is accelerated by solving.
I guess I'm not fully understanding. Why do you need to solve the Fokker-Planck equation if you're already tracing particles through your box? Maybe I'm missing an important step here, but if you just integrate a bunch of particles, you can just bin them and have a spectrum and you're done. Why do you need the Fokker-Planck equation?
You mean I can directly solve the project with the particle?
Yeah.
Okay, that is a good question. Because in lower energy range, the gel radius of the particle is very much smaller than that of the turbulent magnetic field inside the simulation domain. So it is very hard to calculate the evolution of the cosmic ray acceleration in such an energy range. So we assume the subgrid model, subgrid scale turbulence exists inside the simulation box. Okay. And we phenomenologically model the acceleration coefficient.
Okay, then why do you need test particles?
Sorry?
Then why do you need test particles? You could be just solving the Fokker-Planck equation. Maybe I'm just missing something very basic.
Fokker-Planck only in momentum space?
Yes. Yes.
In the real space, they are advected with the velocity flow. Is that what?
Yes, advect.
So there is no effect of the subgrid turbulence on actually spatially confining the particles.
Yes, exactly.
Okay. Then maybe the most important second question. What's the effect of the jet in all of this? So if you removed the jet from your simulation and just did the acceleration in turbulence, how would the answer change?
So in our calculation, we do not treat the, Fokker-Planck equation in the jet region, because there is an uncertainty of the high sigma region in GRMHD simulation. So we remove that region from the calculation of the Fokker-Planck equation and the subsequent neutrino emission.
Do you expect it should make a difference? Would it make a difference? Should we be including it?
I think it may affect, but the time scale, in the jet region, the tracer particle will move fast and then escape from the simulation domain quickly. So I expect that it does not significantly affect the spectrum, but
it's also a place where it gets a boost. So in principle,
a boost.
You can gain energy. Okay, sorry.
Yes, if there is Lorentz boost, yes, it may affect. Yeah.
So I have a question about your injection prescription. So if I read this formula correctly, it looks like it would also inject if your beta is very high, because this maximum will peak 1. Is that, I mean, at high beta, you don't expect reconnection to produce seeds for further acceleration.
So you mean that this one?
Well, if beta is very high, then the maximum will peak 1, and then it would still inject, I expect, a lot of seeds for reacceleration. This doesn't seem very consistent.
Not very consistent.
Yeah, I mean, at high beta, you would not expect, I guess, the efficient ejection. So why do you need this 1? And is this important for what comes out? Because most of the disk is high beta, I suppose.
Yes, we how to say, in the region of the low beta region that is in the interface of the accretion flow and the jet and something like that, we do not consider such a very low beta region. So we just set the upper limit shielding of the low beta region. And this is because, partly because the low sigma region is not so, how to say, reliable in GRMHD simulation. And so we just set the upper limit for simplicity.
But if you would ask the question, like, where most of your high energy protons that you produced in the end were injected, did most of them come from the jet sheath, or did most of them come from the bulk of the disk?
Yes, the acceleration in such a transition region may be very important. So we will we have to consider such a how to say acceleration. So we will address that in future work.
Right. Thanks for a very interesting talk, and let's move on to